Let's begin. Okay, so the topic is time response. What we mean by time response is the following. We have a system described by a transfer function or something like that, that has an input and it has an output. Input, usually we call it u of t, and the output we call it y of t. System is described by a differential equation or by a transfer function. They are equivalent. So the input is something like over the time, that changes over the time. This might be arbitrary, but we usually select things like step input, impulse input, regular inputs kind of, but it can be, anything like a strange function. And that will be an output function. Sorry, this is t. This is y of t. The system will respond to this, whatever. We want to find the relationship between the input and output given the system. We assume that we know the system in terms of its transfer function. We will start from the simpler kind of systems and go to more complex ones and try to understand the response, how these systems respond and what parameters are necessary. We will start from the very simple system, the static system. Which is actually zeroth order, we can say. This is not a real system, but output is simply y of t is simply some constant k times u of t is the what we call the system, and this parameter k is the steady state gain of this system, as you can imagine. Steady state gain. Well, this is not a dynamic system. It is a static system, as we have said. No dynamics here. No time dependence, let's say. Output follows the input exactly. Input multiplied by a constant, which is the steady state gain. This system is always at steady state, actually. It's not a very interesting system. It's just output is a scaled version of the input, okay? So, we sometimes use such systems as approximations, but real physical systems, well, except for steady state, you don't have this kind of time response, okay? But as an approximation, it is possible. Then we have the first order systems. This is more interesting. First order systems are described by first order differential equations. The differential equation with respect to time is first order, and the transfer function g of s is defined by k over, the typical thing is k over tau s plus 1, which is output divided by the input. Okay. Let me give you some examples. For example, the RC circuit, which we have analyzed before, is a first order system. This is VI, this is VO, this is R, this is C, okay? This system has a differential equation of RC dVO dt plus VO is equal to VR, for example. Okay. Similarly, a tank system, a fluid flow tank with QI as input, and a output resistance, let's say, this is the H, this is R. It has a, let's say, area of A. This system, for example, would have, if this is, let's say, is QO, output is QO. If it is QO is your output, then you can actually write the following equation: AR dQO dt plus QO equals QI of T. So it's again a first order differential equation. Okay. You might have a thermometer inserted in a bath, which was the midterm question. Okay. Like this, let's say, thermometer. This is the temperature of the thermometer is T. This is the bath temperature. So RCD dB, and for example, by the way, for this tank system, if you want to write the equation in terms of the height, the equation would look like ADH dt plus 1 over R H over R equals okay. This is the if the output is H. Here output is QR. So you can see that we select our outputs as we wish. And let's select a mechanical system. Let's say let's say that we have a damper and then we have a spring. This cannot be a real mechanical system. This is a approximation again. Let's say this is XO, this is XI. Okay, this is K, this is P. In this case, the equation of motion, if you write it, this will be dXO dt plus XO is equal to XI, would be a first order system. Okay. So as you see, in all of these, we have certain parameters such as, let me do this RC, this AR, this RC again, this is thermal, and this B over K, for example. Actually, all these things I have encircled can be called a tau, which is kind of the time constant of the system. Okay, and then there is a possibility of having a steady state gain. So the general first order system equation is something like this. Generally, you have tau times, let's say, dy dt plus y equals k times u of t. Now, these things have a certain name. This tau is called the time constant. And this is called the steady state gain. So first order systems can be represented by two parameters. Actually, the most important parameter is the time constant. Then there is the scaling parameter, which is the steady state gain. Now, the steady state gain is the steady state gain because when things are settled down at steady state, let's remember that steady state means d by dt, the derivative terms go to 0. So this term goes to 0, and we have y is equal to ku. We have a zeroth order system when things settle down, if you like, and this is the, as you know, this k is the steady state gain, the term that multiplies the input to obtain the output. The transfer function, as I have written above, the g of s is y of s over u of s is equal to k over tau s plus 1. This is a typical transfer function. You might have it, given like this, or you might have it given as, or let's say, g of s might be given to you as some b divided by, s plus a. Okay. Now these two systems are equivalent to each other because you can equate them to each other and say that this b over s plus a can be written as b over a plus, let's say, 1 over as plus 1. And if you compare these two, you see that k is equal to b over a, and tau is equal to 1 over a. Okay. So in this system, if you remember, there is a single pole of this system, which is the solution to this denominator equation, tau s plus 1 equals 0, the value which gives you. So the pole is equal to at minus 1 over tau, or which is equal to minus a, actually. Okay, so the system has a pole which can be represented in the complex plane at here, which is minus 1 over tau, which is equal to minus a. Okay, this is the imaginary axis, this is the real axis. So we talked about the time constant. Let's try to see what kind of effect it has on the system response. And for that, let's look at this thermometer example, which was your midterm question, by the way. The thermometer has mercury in it, and you insert it inside a bath with a temperature of TB. This thing has a temperature. The thermometer has a temperature of T. The thermometer measures its own temperature, as you know. So the thermometer temperature is T, not TB. But eventually, it will be in equilibrium with TB, and it will measure the temperature of the bath. So the T of S divided by TB of S is, as we know, is a first order system, tau S plus 1, where tau is the thermal resistance of the thermometer times the thermal capacitance of the thermometer. Well, we want to find the response of this system when the thermometer is suddenly inserted inside the bath, and we will assume the following, which might not be very realistic, but assume that TB of T is 1 for T greater than 0, okay? So the bath temperature is 1. That is, well, it can be, you know, instead of 1, it can be 30 or 50 or whatever, but let's have it 1, so that we will have TB of S, bath temperature in Laplace transform is 1 over S. So the thermometer is suddenly inserted into the bath, and its own temperature is 0, let's say. Okay? It doesn't matter. We can assume a finite temperature, but just to make things simpler, T of 0 is 0. So the T of S from the above equation is K over tau S plus 1 times 1 over S, right? Which is TB of S. From here, it is this equation. So we can write this as, let's say, K over S times tau S plus 1. Well, we want to put it into partial fractions, but if you want to do it in partial fractions, you have to write it like this, K over. You have to leave the S term alone if you want. S times S plus 1 over tau. This is the same thing. We divided everything by tau. So this would be equal to C1 over S. I'm just separating the denominator terms, partial fraction expansion, S plus 1 over tau. Okay. And if you do the partial fraction expansion, C1 will be K, and C2 will be minus K. You can do it yourselves. I'm not going to do it. So T of S is going to be K over S minus K over S plus 1 over tau. This is what we get for T of S, and the time response of this system is the inverse Laplace transform of T of S, which is easy. K over S is K. Minus, this is K times e to the minus 1 over tau times T. So you can write it as T over tau if you like, or you can write it as K parentheses 1 minus e to the minus T over tau. This is a typical step response of a first order system. If we plot it, we will get such a plot. I say this is T of T. K is the value eventually it reaches. When things settle down for large values of T, it reaches here. The thermometer response will be something like this. Let me draw it. It, you know, reaches to the steady state value exponentially, and it eventually becomes very close to the value. Or it depends, it might be a bit slower, for example, like here. Or it might be faster, like Well, the speed of this response is all determined by the time constant, as you see. And usually, well, not usually, exactly all the time, this means small time constants. Small time constant means a fast system, and a slow system means a large time constant. So the large time constant determines the speed of the system. Tau is, but I should say not tau, but 1 over tau is proportional to the speed of the system. Speed of settling, let's say. When you put a input to a system, that depending on the time constant, it can, reach to the steady state fast or slow. If it has a small time constant, it reaches the steady state fast. For example, if you have a thermometer, the thermometer usually is a very small object, so it has a small time constant, and it, measures the temperature. We are talking about a mercury thermometer, of course, an old type, not the new ones, which are what are they called? They are not ultrasonic, but they are what it is. Anyway, they measure the. I forgot the term. Anyway, now the system reaches to a steady state when there is around, let's say, t equals approximately 4 time constants, okay? So if you have, for example, if you reach here, this means approximately, this range is like, for this green line, this is approximately 4 time, in 4 time constants, the system reaches the steady state, or for this white system, for example, this would be 4 time constants, as you see. So a system with a small time constant reaches the steady state fast. Okay, so this is a typical response of a first order system. So a first order system is determined by 2 parameters in general. K, which is the parameters. K determines the steady state value, and the time constants determines the speed of the response. Okay. As you can see, these are the main things. One thing that I want to tell you is that in general, the steady state gain, K, can be negative. For example, K can be minus 10. What does this mean? For example, when you put an input, step input to a system, the response will be, if this is K, this is Y. In this case, the response is going to be, negative value, like K. Okay. K is a negative number. For example, When you have an air conditioner, let's say, you turn on the air conditioner, and in the summer, the air conditioner decreases the temperature of the room. So the gain of the air conditioner is a negative number, for example. Okay? There is nothing magical about it. Only thing is that the response gives a negative value with respect to the starting value. Okay, this is starting value does not have to be 0, but it can be anything. But the value in the steady state is less than the starting value. Okay. So much for the first order systems. They are relatively straightforward systems. And one thing we should note is that first order systems don't have any oscillations. No oscillations. So the system response does not make, up and down kind of response. Just as in the case of vibrations, this is a smooth increasing or decreasing response is what we have from a first order system. Okay. Any questions up to here? If not, let me go to second order systems, which are a little bit more complex. A typical second order system, as you all know by now, is a mass spring damper system, as you know. So the equation of motion for this system is mx double dot plus bx dot plus kx equals f of t. And the transfer function, which is output divided by the input, force, let's say, is the input, is 1 over ms squared plus ps plus k. There are other second order kind of systems. For example, an electrical second order system is the following. An RC circuit with an inductor on it, let's say. This is again, this is VI, this is VO, this is C, this is L, this is R. I'm not going to derive it, but you can derive it yourself. G of S, which is VO over VI of S, will be so it's a second order system. Or a two-time system would be a second order system. Two capacitances will be a second order system. I'm not going to go into that. It is possible to have all sorts of different second order systems, but the standard form for a second order system is the following. You have seen this in other courses probably. The G of S, which is the output over input, it is K times, K is again the steady state gain. Omega n squared is the natural frequency, S squared plus 2 zeta omega n s plus omega n squared. Okay. So we have three parameters here, as we see. K is the, again, steady state gain, as before. We have now two different parameters. Omega n is the natural frequency of this system, whose unit is radians per second. And then you have the damping ratio, zeta, which is unitless. Natural frequency measures the speed of oscillations or the period of oscillations, and damping ratio measures the how damped your system or the speed of your system. Now let's go to the mechanical system we had over here, this one, okay? And let's try to express it in terms of these parameters we have over here. The mechanical system is G of S. I divide everything by M, by the way. So it is 1 over M, S squared plus B over M, S plus K over M. Okay. Now, compare these two things. We see that obviously K over M has to be omega squared. So omega n squared is K over M. Okay. So we have B over M. Let me just do the following. We have three things, 1 over M, B over M, and K over M. Now, we found that this is omega n squared. Let's look at this B over M, 1 over M, I'm sorry. 1 over M can be written as, if you like, 1 over M times, we multiply and divide by K. So we get 1 over K times K over M. But K over M is, what was K over M by our definition? Was omega n squared. And this 1 over K, if you look at it, the above term, this has to be our steady state gain. This has to be K. So 1 over M can be written as K times omega n squared. Okay? K being our 1 over small case K being our steady state gain. Then for the damping ratio, what do we do with this B over M term? Well, we have the damping ratio, zeta. Zeta, by definition, is the following: B over B critical damping. The critical damping is the value at which the system damping is at the critical, and it is defined by, as we will see, 2 times root mk. Okay. As we know, this B over M over there above is, we define it as 2 zeta omega n. B over M is equal to 2 times zeta times omega n, which is equal to 2 times zeta is B over 2 root mk, okay, times omega n. Omega n was root k over m.
Hocam, can I ask a question?
Yes.
About, hocam, in the damping ratio equation, if we have m equivalent and chi equivalent, we normally use damping ratio is equal to b divided by 2 square root of m equivalent times q equivalent, right?
Yes.
So what if we have like b equivalent? Are we gonna use b equivalent over the same thing, or it is directly b?
I didn't get the question very well, but
Hocam, Türkçe sorabilir miyim?
buyurun.
Hocam şimdi normalde formülümüz damping ratio eşittir b bölü 2 kök içinde m equivalent n k equivalent ya hocam. Normalde bu sistemde b equivalent oluyor değil mi hocam? Biz
Tabii.
burada b equivalent'u mu koyuyoruz b yerine, yoksa normal direkt bildiğimiz b'yi mi koyuyoruz?
We use B equivalent. We use B equivalent.
Okay, thank you hocam.
You know, yes. I'm, you know, I'm trying to derive this for a simple case, but whether you use an equivalent damping or a, you know, damping doesn't matter. You see this k terms cancel, and root m times root m is m, so it is b over m. As you see, 2 zeta omega n is indeed b over m. So this checks. Okay, b over m is 2 zeta omega n. Zeta is therefore, if you like, zeta is equal to, you can write it as b over 2 m omega n, which is b over 2m times omega n is 2 root k over m, which is b over 2 root mk, as you know. So this checks again. So everything is okay. So in short, our parameters for a mechanical system are: the steady state gain is 1 over the spring constant. The natural frequency is root k over m. And the damping ratio is b over 2 root mk. Okay. Second order systems have a richer kind of response. It all depends whether the response is oscillatory or not. Whether the response is oscillatory or not depends on the damping ratio. I will go over this in the next lecture, but let's say that we look at the step response of a second order system. Okay, and we will look at the case where you have the damping ratio is between 0 and 1, which is the underdamped case. In the underdamped case, you have oscillatory response. Okay, and for the underdamped response, you have the following kind of response. If the input is u of t is 1 for t greater than 0, then u of s will be 1 over s, okay? And then y of s will be k omega n squared, s squared, sorry, not s squared, s times s squared plus 2 zeta omega n s plus omega n squared. You can find the partial fraction expansion of this and invert the transform and so on, but this will take a lot of time. I will just give you the result of this. The result will be something like this. Y of t is k times minus where omega d is omega and root 1 minus theta squared, which is called the damped natural frequency. And phi is the so-called phase angle. If you want to plot this, the response will look like this. This is the time response. This is y of t. So you put an input to your system. The steady state value will be k. Okay, input is 1. The output will be k. And the response will look like something like this. It will eventually settle down. But the response is oscillatory, as you see. It oscillates between certain values. Like starts from 0, settles at the steady state, but it makes up and down kind of motion or back and forth kind of motion. This is a typical second order system response. Actually, the response depends on the damping ratio. First of all, the period of the oscillations, as we all know, the period is like, this is the period. The period of oscillations is 2 pi over the damped natural frequency, okay? And it is a constant. And the amplitude of oscillations depends on the, well, on the damping ratio to a certain extent. Damping ratio actually determines the character of the oscillations. Damping ratio, let's say zeta. If zeta is 0, you have an undamped system. If 0 is less than zeta less than 1, you have an underdamped system. And as we know, underdamped systems are the most important for our case. If zeta equals 1, you have a critically damped system. And if zeta is greater than 1, you have an overdamped system. Okay. Now we can find this from the poles of a system. S squared, this is the denominator polynomial, 2 zeta omega ns plus omega n squared equals 0, gives you the poles. And if you solve for this equation, you are going to get the following poles. S12 equals minus zeta omega n plus minus omega n root zeta squared minus 1. Okay. Now, depending on the value of zeta, the poles might be real or complex. When zeta is 0, for example, the poles are what? This is 0. Omega n times root minus 1 is j, okay, plus minus j omega n. They are purely imaginary roots, okay? And if zeta is in between, let's say, 0 and 1, S1, 2 is minus zeta omega n plus minus, again, j omega n root 1 minus zeta squared. As you see, since zeta is less than 1, the term inside here is an imaginary number. So we take a j out and reverse the sign, as you see. If zeta is 1, so you have S1, 2 is equal to 1 minus 1 is a 0. So you have minus omega n. So you have repeated poles, okay? Two of the poles are at the same place. And if zeta is greater than 1, you have the same thing we have over here, S1, 2. Minus zeta omega n minus. So this is purely imaginary. This is complex. This is repeated, and this is real. So if you want, let me stop just by doing this. Let me plot the poles in the complex plane. Poles in complex plane. This is the imaginary axis, if you can, if I could draw it. There has to be a way to draw it nicely. This is the real, this is the imaginary. Okay. When zeta is 0, the poles are here. You know, this is j omega n. This is minus j omega n. So this is for zeta equals 0. Then the poles, when they start moving like this, as damping ratio increases, like this supposedly makes a circle, although I cannot draw it very well. And it comes to here when zeta is equal to minus omega n. Okay. So here you have zeta equals 0. Here you have 0 less than zeta less than 1. Here you have zeta equals 1. And then one of the poles go like this. They become real and go in this direction. Obviously, the systems, the responses will look like this. Let me just verify. If you have zeta equals 0, the time response will look like purely oscillatory. Okay. I have drawn the zeta equals underdamped. For overdamped, the responses would look like this. They are a little bit like, this is zeta is greater than 1. And for if zeta is equal to 1, you have a kind of a fast response. But if these responses are non-oscillatory, okay, and you know when you have underdamped response, you have oscillations like this one. This is 0 less than 0 less. These are all time responses of the system. Okay, let's stop here because we are getting late. Do you have any questions?